Fine.
No.
All right. Good afternoon, everyone. Let's get started. It's a pleasure to have Professor Yanofsky give us part two. Today will be all the juicy details of what you saw yesterday. We are really looking forward to it.
No, it's a totally different talk, but related in a certain sense. We're looking for structure. That's what we're looking for. Okay, so it's called theoretical computer science from the category theory perspective. Okay, and basically what I'm trying to do is sell theoretical computer science and sell category theory, and show you that I hesitate to use this word. The right way to learn theoretical computer science is through category theory, and you'll see why. Okay, we describe the structures of the collection of computable functions. We show how category theory, I'm sorry. I gave that survey of what you know and what you don't know. I took it into account. I'm going to get most of you to, I will talk to most of you. So you're going to define every single word I use, including computable function. We show how category theory is fundamental for understanding the major ideas and theorems of theoretical computer science. Computability theory and complexity theory will be our main focus. Those are the two main branches of theoretical computer science. We will meet some of the deepest notions of modern computer science and mathematics. Turing machines, unsolvable problems, the P equals NP problem, Gödel's incompleteness theorem, intractable problems, cryptographic protocols, Alan Turing's Halting problem. We're gonna talk about all these different topics. Okay, so here's the outline. I'll give you an overview of what this is all about, then we'll talk about models of computation. Then I told you the two main branches are computability theory and complexity theory. Then I'm going to give you something called the diagonal theorem. It's a small theorem in category theory, and a lot of results fall out of that small theorem. It's an amazingly large, not just results, important results. And then not only something I call complementary capitals. Well, we'll see it when we get it. Okay. So, background. So I wrote this wonderful book. It's called Monoidal Category Theory. You have the picture there. Okay, wonderful book. And I spent a long time doing it. And the book is not only it's not about monoidal categories. It's about, first before I start off with monoidal categories, I start off talking about category theory. And before I start off category theory, I talk about sets. What's a set? What's a function between a set? And you get a lot of intuition by just looking at sets and functions between sets, and we'll get there. But I wanted to make the book very more interesting. And so what I did was I added in little mini courses, 13 mini courses into this thing. And the mini courses are not ways of teaching you new category theory, but it basically at the end of every chapter, stop. And I teach you a college course from the point of view of the category theory that you already learned. And so we have a category theory on basic linear, a mini course on basic linear algebra, self-referential paradoxes, categorical logic, lots of these advanced linear algebra, duality theory, quantum groups, which is something physicists are interested in, database and scheduling, which is something computer scientists are interested in, homotopy type theory, knot theory, lots of different mini courses. One of the mini courses I was writing was theoretical computer science. And so I sat down to write this mini course, and I wanted to cover some of the main topics in theoretical computer science. The thing was, it just went on and on. It took me a while to get the definitions right, but once I had the definitions, this mini course, which was supposed to be 30 pages, went to 40, 50, 60, 70, 210 pages, okay? And I was able to get a lot, at least state, or prove and state a lot of what's taught in a first-year graduate course in theoretical computer science or something like that, or maybe an undergraduate. So, but I didn't want my book to be all about that. So I excised, I took out the theoretical computer science part and I made a book out of it. It's called Theoretical Computer Science for the Working Category. Okay, the title is a joke because the main book in theoretical computer science, in category theory, is by one of the founders of category theory, namely Saunders-MacLean. And Saunders-MacLean wrote a book called Categories for the Working Mathematician. And the idea is, if you know mathematics already, he'll teach you category theory. Okay, so this was along the lines the same thing. If you know category theory, I'll teach you theoretical computer science. So that was part of the mini course. It was 210 pages, but Cambridge said they won't publish 210 pages because they wanted to keep this series like a cheap, short series. So they published 150, and the rest of it I excised and put it in on my webpage. And so that's why I call supplementary chapters. So that's what we're about. When I was younger, I wrote Saunders MacLean a letter, and I asked him permission. His book was called Categories for the Working Mathematician, and I wanted to write a book called Mathematics for the Working Category Theorist. In other words, if you already know category theory, can I teach you mathematics? And he said yes. And I said, can I use your title? Can I use that title? And he said yes. But I never did. Okay. But I like that. Okay. So now I'm going to do two parts. First, I'm going to motivate theoretical computer science, and then I'm going to motivate category theory. And then we're going to marry them together. Question, what is theoretical computer science about? Answer, computable functions. So what's a computable function? These are the set of functions that can be mimicked by a computer. So let's go through this. What's a function? A function is a rule that from this set to this set, that every single element in this set gets an element in this set. Okay, that's what a function is. Well, you want to know a computer can do that rule. Can you give it the input, you give it the output. What computers do are they mimic functions. Okay, you have an input to the computer, you have an output to the computer. Okay, and that's the same thing as a function. So this is the most fundamental part of today. So you have the set of all functions, and then you have some of them which are computable functions, and that's what we're aiming at studying. Now, there's a subset of those that are very important because a lot of times, especially when I program, the computable functions become infinite loops at some times, okay? Which means that there's certain inputs that don't have an output, okay? Happens to me all the time with my programs. Anyways, the point is, so those, we call those computable functions, although really they should be called computable partial functions because sometimes you have an input that you don't have an output. So there's a subset of computable functions which are called total computable functions. Okay, so now keep this Venn diagram in your head. You have all functions, then you have some of them are computable functions, and some of those are total computable functions. Very important. Okay, good. So what are computable functions? Functions that can be mimicked by a computer. Okay, what's computability theory? Now we're talking about different areas of theoretical computer science. We ask the following questions. What functions are computable? More interestingly, what functions are not computable? So I gave you this three-part Venn diagram, and now I'm asking you what's in the computable functions, what's not in the computable functions. And that's a major part of theoretical computability theory. Next comes complexity theory. What's that about? What functions are efficiently computable? And more interesting, what functions are not efficiently computable? What takes longer time to do? So these are two branches. Now, there are other branches of computer science, of theoretical computer science, automata theory, formal languages, analysis of algorithms, data structures, cryptography. I have a supplementary chapter on that. Quantum computing theory, that's a hot topic now. Logic and computer science. There's a lot of different other topics of theoretical computer science. Question, how do you think of computable functions? Okay, how should one think of computable functions? So I'll give you 4 or 5 answers to that question. 1, think of them as computable functions. You know what a function is. So this is a function that happens to be mimicked by a computer. Great. Next, another way to think of it is functions computed by Turing machines. So now we're talking a little history. So Mr. Turing, Alan Turing, was an Englishman who came to Princeton in the 1930s to work under a guy named Alonzo Church. And he wanted to formulate, or he wanted to discuss what a computer can do and what a computer cannot do. Okay, and so he came up with something which we now call a Turing machine. I'm going to go through a little bit of what a Turing machine is, but the main idea is it's this little device that goes back and forth and can compute different things. Okay, I have to tell you his motivation. Okay, where did he think of the Turing machine? And the idea is as follows. We're going to see this over and over. People think of things as their most, as the most important technological development. So in the 30s, people on Wall Street used to communicate with each other with something called ticker tape. Okay, ticker tape is there would be a long roll of paper and there would be a printer and the printer would say IBM 38.7. And you watch movies from the 30s, you see this. You know, this stock was this amount. And the point was you were able to communicate. So it was a little printer and you were able to communicate all types of information on this thin line of paper. Okay. You hear this phrase, nowadays you hear the phrase, a ticker tape parade. What's a ticker tape parade? Yeah. Okay, so it used to be that whenever there was a parade in New York City, it was down the main street in Wall Street, okay, and it was called the Canyon of Heroes. So with tall buildings, and people would go down and people would throw nice things at them to show that they appreciate them. So one of the things they would throw at them were these used up tapes from this machine that would be a ticker tape. So they would throw it out the window and it looked very cool as it went down. So that's called a ticker tape thing. Anyways, so Turing was very impressed with this fact that one strip of paper can communicate all these types of things. He was also very impressed with typewriter ribbons. Because if you look at a typewriter ribbon, it's a one-dimensional object that has every single possible thing that you can write. So he was using that. Anyways, so basically, Turing invented this object called a Turing machine, which manipulated strings of characters. I'm not going to get into exactly, but it's a way of doing it. Okay, now there's something called the Church-Turing thesis. So let me give you more history. So you're all working with mentors and things like that. So Turing came up with this idea, and Church comes to him and says, by the way, I'm making this up, but it's not far from true. Turing comes up with this idea, and he shows it to his mentor, Alonzo Church. And Church says, oh yeah, can you do multiplication with your machine? And Turing would go home and come back and show him, yes, I can do. And Church would say, oh, wow, that's pretty cool. Can you do division with this thing? And he would go home and he would show him, you can do it. And then he would say something, could you do recursion with this? And you go back and do recursion. Can you do this? Can you do that? Whatever. And every single thing he did, okay, every single thing that Church asked him to do, Turing was able to do. Can you do subroutines? Yeah, I can do subroutines. Can you do this? Can you do that? Can you compose functions? Yeah, I can do that. Okay, anyway, so at some point, Church and Turing said, you know what? I think you got it. I think this device can do whatever's computable can be done by your device. Okay, now you have to understand, this is said in 1930, let's say 5. There were no computers then, so there was nothing to compare. So this is called the Church-Turing thesis, which says that whatever is computable by a Turing machine. Okay, now it's not a theorem, it's a thesis. It's just a statement. Why isn't it a theorem? Why can't you make a theorem out of this? Okay, and the answer is because we don't know what is computable. We don't have an exact definition of what is computable. I could tell you exactly what's done by a Turing machine. I could show you what it's done, but I don't say, so listen to what the statement says. Whatever is computable by a Turing machine. It's a little bit hard to say what's computable. Okay. Meanwhile, 90 years later, no one has ever found anything that their computer can do that a Turing machine can't do. So far it seems to be correct. And again, it will never be proven because you don't have, you're comparing two things of which one of them is an informal discussion. Okay, now you might say, oh, whatever's computable by procedure. No. Or whatever seems computable. Well, what we're going to do today is show you a lot of examples of things that would seem computable but are not. Okay, next. So this is in the 30s. Next thing is called, and most people don't know what this is, and that's fine because I didn't know what it was either. It's called the register machine, and this is the idea. People in the 50s and the 60s said, you know what? It's a computable function, something that you could write a real program for. Okay, you're all sitting in front of computers. You all know, and this is the 50s, 60s. They're dealing with COBOL. They're dealing with PL1. They're dealing with assembly language. So what they decided to do was say a computable function is a function that one can write a program for. So instead of talking about Turing machines, they talked about what one can write a program for. And basically, the programs manipulated not strings but natural numbers. Okay, they manipulated natural numbers, and we'll go through more of the definition. Anyways, there's a theorem. Whatever. Oh, this is a song that I teach my classes when we do it. We'll do it together in chorus, and you can bury your pride. You're not on the camera. Okay, whatever you can do, I can do better, or whatever you can do, I can do equal. Okay, and so this concept shows up over and over in theoretical computer science. So you ready? First song. Whatever a Turing machine could do, a register machine could do. Whatever a register machine could do, a Turing machine could do. Okay, so they're computationally equivalent. That's what it's called. Okay, great. Then comes a little later, and people start talking about, you know what a computer is? A computer is, I'm sorry, what a computable function is? A computable function is something that a computer can do. Well, what's this computer made out of? Logical circuits. So they started talking about logical circuits and what can a computer do, okay? And okay, now comes the song, ready? Whatever logical circuits can do, a Turing machine can do, a register machine can do, whatever, etc. The opposite also. Okay, great. Okay, then comes the logicians. They always come in and they always have to make things a little bit more complicated. And they said, you know what, if a computable function, something that can be described by logical formulas. We're going to talk about this, but we're not going to get into that. But you'll see that all these are models of computation. Let's go through what that means. A model of computation is, you want to say a computable function is a function that can be computed. Well, what does it mean to be computed? It means either by a Turing machine, a register machine, a logical circuit, or a logical formula can describe it, et cetera, et cetera. So these are called models of computation. Main point, there's a line. It goes like this. It's an early computer scientist. He said like this. He said, saying that computer science is about computers is like saying that astronomy is about telescopes. Okay, astronomy is not about telescopes. Astronomy is about stars and celestial bodies. We look at them. We look at these stars and celestial bodies through telescopes. Okay, same thing here. Theoretical computer science is not about Turing machines. They're not about register machines. They're about computable functions. Okay, and we're going to stress that over and over. They're about computable functions. We deal with them by programming, by writing by making electrical things, but really it's about computable functions. Okay, we spend a lot of time. Question, why category? Okay, so now the second part of the overview, why are we doing this? Why am I pushing category? And I'm giving you 6 reasons, but 5 reasons. 1, it's easy. Okay, most of the ideas and theorems of theoretical computer science are consequences of the categorical definitions. You'll see it falls out once you get the definition straight. It falls out of it. The concepts of theoretical computer science simply emerge. Many theorems are straightforward consequences of composition and functoriality. So I'm going to go through what those 2 words are. The main part of a category is that there's compose. You can compose morphisms in a category. You can compose functions in a category. That's that. And the second main point about category theory is functoriality. What's functoriality? Between two categories, you don't have functions. Let's go through this carefully. Between two sets, you have functions. Between two categories, you have functors. And functors respect composition. Okay, so that relates two different areas very well. So you have a category here that has some interesting structure. You have a category here that has some interesting structure, and there's a function between. Okay, it's short. The powerful language of category theory ensures us that what is usually taught in a large textbook can be taught in a 150-page. Okay, it's short. It's much shorter, and it's done nicely. It gives you the right perspective. Anyone who has ever experienced any category theory knows that it makes you zoom out and see things from a bird's eye view, rather than getting overwhelmed by all the little details so that you cannot see the forest for the trees. Category theory lets you see the big picture. And I'm going to show you the big picture in a few minutes, this big picture. But always, category theory always gets you to understand things much from a higher perspective. I remember my thesis advisor, whatever, I worked on a project. He went away for the summer. He came home after the summer, and I showed him what I was doing. And then he looked at it, and then he said, "Oh, so what you did was blankety blank 3 sentences." He took my entire summer vacation and summed it up into 3 sentences, because I was looking at it from here and he was over here, and I had to process those 3 sentences. And I said, "Yes, but I might have made some wrong turns along the way." And he said, "Very nice." And then he sent me out of the office. Okay, graduate school is painful. Next. Question, why category theory? 2 more things. It gets to the core of the issues. Category theory distills the important aspects of subject and leaves one with the main structures needed to understand what's going on. Okay, now for the main thing for you. You're a physicist. So let me tell you, it connects better with other areas of science and math. Category theory has become the lingua franca of numerous areas of mathematics, and theoretical physics. By putting the ideas of theoretical computer science in the language of category theory, connections are made to these other areas. And he's going to talk a lot about this, why category theory is very important for physics and many other areas. Okay. I started graduate school in 1991. 2 or 3 areas mention category theory. Now category theory is much more prevalent in mathematics for sure, in physics, in computer science also. It shows up a lot. Okay. Okay, so this is the picture that we're gonna do. Now, I know you're gonna be angry because yesterday I gave you out some nice things. So here's just to pass it along. It's just this picture, but I want you to see it, and if you want, you can write up on it, et cetera, et cetera. This has everything. So this is the big picture of models of computation. Now, I'm going to spend 15 minutes going through, orienting your way around this and going through what each one of these are categories, and the little arrows are morphisms between them. Okay, so let's go through it. Ready? You have functions, computable functions, total computable functions. That's that 3-level hierarchy I told you about. You have all possible functions, you have a subset of all possible functions called computable functions, and you have total computable functions, which is those functions which always give you an answer. Very good. Now you have 3 spokes, spokes as in a bicycle, spokes, 3 spokes coming out of that. Okay, 1 spoke is about Turing machines, 1 spoke is about register machines, 1 spoke is about circuits. Okay, and we're going to go through each one of these spokes separately. But then once we do this, we're going to go through these 2 very quickly, and we're going to focus on these. Why? Why focus on those rather than the other 2? Simply because the vast majority of you wrote down that you know what a Turing machine is. Okay, so we're going to focus on Turing machines and not the other ones. But here's the point. It doesn't matter. It's all the same. Okay, whatever a Turing machine could do, a register machine could do, a circuit. But these are just three ways of talking about the same things. Okay, let me give you the idea behind it, and then we'll get into the details. The idea is this is the main topic of conversation: functions, computable functions, and total computable functions. And the idea is a Turing machine is a computer. It has inputs and outputs. So what you have is for every Turing machine, every single Turing machine, there's a computable function that's associated to it. Right? What's the input to the Turing machine? What's the output to the Turing machine? Okay, so this is going to be the set of all Turing machines, it's going to be the category of all Turing machines, and for there's a function from here to here. Namely, for every Turing machine, it describes some type of function. If I put something on the input, what will I get on the output? That's a function. Okay. Same thing here, same thing here. Great. So let's go through these parts. Okay, so here I'm highlighting, this is the center of the thing. As I told you, this is what theoretical computer science is really about. But you can't talk about a function without mentioning, some way of describing the function. Okay, so great. Okay, so let's talk about the func category. Okay, so now I'm talking about in some sense, the func category is the largest thing, and everything else is like some part of it. Okay, so it's like the category of sets. You were mentioned, the category of sets was mentioned to you, but if you don't remember, that's okay. What's a category of sets? Well, it's about a set here and a set here, and you have a function between them, no problem. But categories, so I'm sorry, we're talking about the category of functions, but just to make things easier for a second, we'll talk about set, because everyone has an intuition of what the category of set's about. So you have a function from this set to this set, but you also have composition. The main positive aspect of a category is you can compose them. So given a function like this and a function like this, you can compose them to get like this. Now, we like computers, so we call this sequential composition. What do I mean sequential composition? You do one and then you do the other. Okay, there are also identities. These are stupid functions that the input is the same as the output. Okay, they do nothing. Okay, but the composition is associative. So if I had three of these, F, G, and H, it doesn't matter how you compose them. And the identities act like a unit. What does it mean? It means if I take a function and I compose it with the stupid identity function, I get back the original function. It's like x plus 0 is equal to x. So function composed with this silly function that outputs the same thing as it inputs is just the original function. Okay, so it acts like an identity. Okay, conclusion. The category of sets, so sets and morphisms in between them and functions in between them form a category because this sequential composition is well behaved. Great. Okay, but it has more structure than just a category. Okay, so it's more than just a category. What is it more than a category? Given objects A and B, think of them as sets. We can multiply them and form A cross B. Okay, A cross B is ordered pairs. Okay, so they're ordered pairs of elements. Okay, and we can multiply, not only can we multiply sets, but we can also multiply functions between sets, morphisms between sets. Let's go through it. If you have a function A to B called F and another function C to D called F prime, then you can have A cross C to B cross D. What you can do is you can apply F to these things in A, which will give you something in B, and you can apply F prime to these things in C, which will give you something in D. Okay? So this is called parallel composition. Okay? Because basically this guy and this guy are running in parallel. Now, again, they're functions. We're not talking about anything computable, but they're functions, but it works very nice to think of them as parallel processing. We have some procedure to do to get this. We have another procedure to do to get this. Therefore, we have a procedure to get both. Okay. This also has an identity, just like identity functions, it doesn't matter, but this is, so what we just said was category theory, the category of set is not only a category, it's a monoidal category. This monoid means you take two things and you bring them together, hence the word monoidal category, and you bring them together and they compose very nicely. Okay, so now we have two types of composition: sequential composition and parallel composition. This book is not called category theory, it's called monoidal category theory, because we like, the whole point is that we bring in this extra amount of structure where we can do things in parallel. Okay, hold on. But it has more structure than just a monoidal category. It has another layer of structure, and then I'll stop. One more. Okay? And the idea is as follows: given objects A and C, there's a way to swap A and C. That is, there's a map that takes A to A and C to C. Okay? Extra dot. Okay? Another way to see it is A goes to A and C goes to C cross A. Okay? And again, think of just ordered pairs of elements. One little a, little c is going to go to little a, little c. Nothing to it. Okay? But we want that this swapping can be done in a systematic way. Okay, and so basically what we want is our parallel computation should be done in a nice way. On the side of your computers, or probably it doesn't even have that anymore. A few years ago, they used to have it. Used to say on the side of the computers, duo processor. What does that mean, duo processor? I don't see it anymore. Okay, it means that your computer has two processors. Okay, so basically what that means is you can have one process running on one, you can have one algorithm running on one process, on one processor, and one running on the other. But you know what else you can do? You can swap them. You can have this algorithm running on this processor and this algorithm running on this processor. And you can do that nicely. So basically what we're saying is that we not only have a notion of composition, sequential composition, we also have parallel composition. And the parallel composition is easy to swap. It's easy to do one not with the other. Okay, now what it means is it has to satisfy this requirement. And this requirement is, well, it's called, the swapping gets along with the other morphisms and sets. Okay, this is also used, the word is natural. And another word is they cohere. These swapping coheres with these things. Let's go through this. You ready? If you have an element in A cross S and you run one of them in F and the other one in F prime, so then you're going to get B cross D. Now you swap the outputs. You put this output over here and you put this output over here. Well, then that's the same thing as first swapping A and C, swap the inputs. Then do this, but not F cross F prime cross F. Swap which processes are doing on which, and you get it. So this makes set into what's called a symmetric monoidal pattern. Most of our things are going to be symmetric monoidal categories. Most of the things we talk about are going to be symmetric monoidal categories because we want a category, we want to compose functions, we want parallel processing, and we want to be able to swap the parallel processing whenever we want. Okay, great. So that's all about the category of set, but let's talk about the category of func. Func is just a subcategory of the category of set. It's a part of the category of set, but we want to make it more computerese. Okay, so when you write a program on a computer, okay, it has types. In other words, I said to you before, computers take inputs to outputs. Well, what type of inputs? So the inputs could be natural numbers, real numbers, strings, booleans, doubles, et cetera, okay? So this is what, instead of saying our functions go from a set to a set, let's say that they go from a type to a type, okay? And those of you know computers, so you have typed languages and untyped languages, and you have this one is easier and this one's not. And we'll push Python, but Python makes it easy to shoot yourself in the foot. There's all types of these statements. So basically, we're going to deal with functions like this that go from this type, from a type, okay, to a type. So this function accepts three natural numbers, and then it accepts a string, and then it accepts a Boolean. You can think of this three natural numbers, your age, your weight, your, I don't know, whatever. What's your name, and 0, 1, whether you're a student or a teacher, okay? And it's going to output your BMI, your, I don't know, whatever and whatever. Okay, great. We're going to shorten this to sequence 1, a sequence of types, to sequence 2, a sequence of types. This category is also a symmetric monoidal category. I did the same thing as I did with sets, but I restricted myself and I say, you know what? I want to talk about things that computers can do, and computers deal with types. Great. Okay, so now let's go here. Hold on. Okay, so now you get a feel for what this is all about. So you have the category of funcs. Let's go through it. The objects are all sequences of types. The morphisms are all functions from one type to another. Then you have a subset of those. The objects are the same objects, sequences of types. In fact, and the morphisms are the morphisms are computable functions that are computable functions. That means a Turing machine can do them, a register machine can do them, a circuit can do them, whatever the hell you want to think about. And then there's a subset of that. Now, I didn't talk about these black lines. This looks like a subset. What it is a function. Okay, but it's not really a function. So we said, what's between two sets, you have a function. Between two categories, you have, the word is functor. So this is a functor, but this functor looks like an inclusion. Okay, it's like a subset. And so we say, this is a subset of this is a subset of that. Let's go through it. All three of them, boom, 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 all three of them have the objects are sequences of types. These are arbitrary functions. These, the morphisms are computable functions. These, the morphisms are computable functions that always start and stop at the finish. Same thing. Great. Let's go through a chart that gives you what I just said nicely. So we have the category of func, the category of computable func, the category of total computable funcs. Okay, the objects are all types, same objects. The functors take the objects to the objects. Most of the time, we're going to have, right. Okay, these are all functions. These are all computable functions. These are total computable functions. And what structure do they have? They're all symmetric monoidal categories. So far, so good. We've got the main spine of our big picture done. Okay, now let's go out. Okay, question. What does, so here's this. Now I want to talk about these. Let's talk about Turing machines first. What does Turing machines manipulate? What do they manipulate? Long strings. Okay, so this is going to be just like this, except I don't want to deal with nats and reals and doubles and all Booleans and all that nonsense. What do I want to deal with? What does a Turing machine deal with? Strings. Okay, you plug in, you have number of strings to deal with. You have inputs onto the strings, you have outputs to the strings. Okay, so this includes into this. Let's go through this. This has all possible types, nats, reals, etc., etc. This has just one type, strings. Same thing here. This has all possible types. This has just strings. Great, that's going to deal with this part. What about down here? Well, what do register machines deal with? What do register machines manipulate? Natural numbers. Okay, and so what we're going to have down here is, I don't want to deal with strings, reals, doubles, Booleans. I just want to deal with natural numbers. Okay, so that's this, because we want to talk about register machines, and register machines only deal with natural numbers. Great. What about this? What do circuits deal with? Answer, bits. zeros and ones, binary, Booleans. Okay, so we want to deal with that. So these guys, they're not interested in reals, doubles, natural numbers, computable strings. They're only interested in zeros and ones. Circuits take zeros and ones and output zeros and ones. That's it. Okay, great. And these functions here are going to be functions from zeros and ones to zeros and ones, but they're going to be total functions. Now, let's think of that. How could you have a circuit? Things come in, things go out. How do you have an infinite loop in a circuit?
You have a latch.
A latch. What's a latch? A relay. Anyways, it's very simple. Your circuits loop back onto themselves. Okay, circuits can loop back onto themselves and you can get an infinite loop. So sometimes you can get an infinite loop depending on, probably need some type of switch. Okay, but fine. Main point. We're just talking about functions. Some functions from natural numbers to natural numbers, from Booleans to Booleans are total, some are not. Okay, so let's talk about, so first we're going to talk about these guys, then we're going to talk about these guys, then we're going to talk about these guys in this chart form. Total, you have computable strings. This is what Turing machines deal with. Okay, what are the objects? Powers of strings. Strings, pairs of strings, triples of strings, four tuples of strings, n tuples of strings. Okay, and what the morphisms? Computable functions. Powers of strings, total computable functions. These are symmetric monodal categories, these are symmetric categories. Very nice. Okay, what about natural numbers? What about register machines? Powers of natural numbers. So this computer takes 5 natural numbers in and outputs 3 natural numbers. This computer takes 17 natural numbers and outputs 7 natural numbers. Same thing, computable functions, total computable functions, symmetric monodal categories. Booleans, same thing. Great. Now, let's talk about the morphisms between them. Okay, the functors between them. Obviously, these guys include into these guys. These guys on the outer spokes include, because why? These have all possible types. These have just one type. Type of strings, the type of bool, the type of natural numbers. So there's obviously the inclusions, but it goes the other way. Okay, so every inclusion has a map the other way. Let's go through this. Let's say I only lived in the world of register machines, which only deals with natural numbers. And I wanted to write, it to work with an LLM and edit a chapter of my book. Okay, now you might say, oh, no, we can't deal with that. LLMs, register machines only deal with natural numbers. I can't deal with strings. But you know it can deal with strings. How do you do it? You encode things. Any type of data can be encoded as any other type of data, period. That's what's encoding. That's what a large part of your time computing, you're dealing with this. You're changing, oh, I have this as a string of bits, but I want it as a natural number or whatever. I have it as a real number. By the way, how does a computer deal with a real number? It's basically a real number is basically 2 natural numbers. Okay, what's before the dot? What's after the dot? So everything can be changed into everything else. So let's go through this. This only deals with natural numbers. Very good. So I have an inclusion of this because this deals with all types, including that. But what happens if I have more complicated structure? Well, I can encode it like this. Now, these are not isomorphisms. In other words, going back and forth doesn't give you the exact same things, but they are related. And it doesn't pay to get into technical details of why they're related, but all of them are related. Great. Good. Let's move on. Let's get to the outer spokes. Okay. So we're going to talk about Turing machines, the category of Turing machines, and we're going to talk about the category of total Turing machines. We're going to talk about the category of register machines, total register machines. We're going to talk about the category of circuits in total circuits. It's the same thing. Okay. Okay. So what's a Turing machine? So we've been talking about Turing machines for 40 minutes, but we didn't say what Turing machines. Usually you think of a Turing machine as one long string and you're manipulating that, but you don't have to think of it that way. Okay? What you could think of it is, here's input tapes, here's output tapes, and the computer might have to figure things out, so he has to work tapes. You have work tapes over there. So this is a more general definition of a Turing machine. Now you might say, oh, wow, this is way too powerful. I didn't learn about these. Okay, I only learned about Turing machines that have one tape, et cetera, et cetera. Okay, first of all, you don't want to deal with a Turing machine with one tape, because those are pain in the necks, because you don't have room for anything. Okay, you like these because you can put up information here, you can put information there, you can transfer, et cetera, et cetera. So you don't want Turing. So they teach you the easy definition of Turing machine with just one tape, but the truth is this is much more better and more things. So this is an M input, N outputs, and K work tapes.
You can always turn one of these into a one tape one, right?
And now you see he's starting to sing the song. You ready to sing the song? Whatever M, K, N Turing machine can do, a one Turing machine can do also. You see? If you would sing it, it would really make the class. So what does Turing machine do? It has eyes looking at all the tapes. Okay, and it says I'm in state Q42. Okay, and then there's rules, there are programming rules that say if this eye sees this, and this eye sees this, and this eye sees this, then change this to this, change that to that, change this to that, do all types of mean and nasty things, etc. Main point. Program starts with the input over here. It's going to do things. If it stops, then the outputs are over here. Okay? If it doesn't stop, then it's a partial function, and sometimes it doesn't stop. Again, when I program something, most of the time it doesn't stop. Okay? But okay, what does a Turing machine do? It computes a function from M strings to N strings. That's what a function, that's what a Turing machine does. It takes inputs of string to the M strings, and outputs N strings. That's it. Okay, great. Guess what you can do with Turing machines? You can compose them. Okay. I don't have the latex skills to compose them, really. Okay. Latex skills is the most important thing. Okay. But basically, I would love this picture to be on top of this picture. Okay. And what I would like is to think of this as sequentially composing Turing machines. So what do? You have an input here, you work out some details, you get the output here. The output here should be the same as the input here, okay? And you work over here, this is a different Turing machine, and you get this different, okay? I would have made this different M inputs, K, whatever. This would be M prime or N inputs, K inputs, would have brought that together. But basically, you can compose Turing machines. You first do one Turing machine, you have the input going to the output, then you take that output and put it into another Turing machine. Input and output. Great. Guess what else you can do? Parallel process Turing machines. Okay, so when you parallel process Turing machines, this Turing machine is going to have N plus M prime inputs. This is going to have N plus N prime outputs, and you can do them at the same time. Okay, what about swapping them? You can swap them. Okay, ready? The objects, oh, okay, so now we're going back and we're talking about this category. Okay, the objects are natural numbers. Okay, natural numbers. Why? Because my inputs, how many inputs do I have? M. How many outputs do I have? N. And so the morphisms between the natural numbers, the functions between the natural numbers are, so a Turing machine from 5 to 7 is a Turing machine with 5 inputs and 7 outputs. Okay, and so if you have a Turing machine from 5 to 7, and then another Turing machine from 7 to 38, then you can compose them and you have a Turing machine from 5 to 38. So that's what that's all about. So the number of inputs and outputs are the objects of this category. Okay. And what are the morphisms? Each morphism is a Turing machine. And this is not a category. It does not form a category. Okay. It fails to be a category. It's something called a bicategory. I'll explain to you what it is. Problem. The composition is very nicely defined. I can define the composition, no problem. I get a problem when I talk about associativity. Okay, when you compose 3 Turing machines, it's different. Think about it as a program. Let's say you have 3 programs and you want to compose one program after another program after another. Okay, you can get in trouble. How are you composing them? Are you composing the first 2 and then the third one, or are you composing like this, like this? It's a subtle difference, but it's a real difference. It doesn't form a category. The idea is as follows: things are a little bit too rigid. Was that too physical? This brings up what we talked about last class. You have to idealize it. Okay, if you don't idealize it, you get this. So it's physical things are not mathematical things. So you need less axioms. Really, it doesn't form a category. Okay, good. Let me tell you what a register machine is. Okay, register machines are methods for manipulating natural numbers. These machines are basically programs in a very simple programming language, where variables can only hold natural numbers. The programs use 3 different types of variables. X1, X2, X3 called input variables, Y1 would do called output variables, and work variables. Okay, so our programs are simple statements like this. Z is some variable, Z is equal to Z plus 1, Z is equal to Z minus 1. If Z is not equal to 0, go to L. That's it. That's the only, so, you know, C has something like 5 different things. The rest is done with libraries. C programming language. This has 3 types of statements. Okay, and guess what? Even though that's a very, very small programming language, whatever a Turing machine can do, this could do. Whatever this machine can do in here, whatever these computers can do in here can be done by a register machine. And it's all from manipulating things. Now, I could talk about composing register machines. There's 2 ways of composing register machines. Again, think of a register machine as just a computer program. It's a sequence of statements. Okay, and I can talk about parallel processing them. Okay, and so again, the objects are natural numbers, namely, how many input variables do you have? How many input natural numbers do you have? How many output natural numbers do you have? There are functions between them. Register machines, total machines, they do form, they don't form a category, but they have a monoidal structure. They don't form a category. Again, you have trouble with associativity. Circuits. Okay, these gates generate all logical circuits. So this is an AND gate, this is an OR gate, this is a NOT gate, this is a NAND gate, NAND, not AND. This is a NOR gate, okay? And you put them together and you get logical circuits. Okay, I just want to say an interesting thing. The computers in front of you mostly work with NAND gates. Okay, they're very easy to implement with everything else. Everything else falls out of NAND gates. So that's a very interesting thing. We'll see that a little later. But main point, this has 1, 2, 3, 4, 5, 6 inputs, 2 outputs. So this is going to be a function from 6 to 2. This is going to be a function from 6 to 2. And we get it. The circuit has 6 inputs and 2 outputs. Guess what? Take a circuit, take another circuit, you can compose them. Guess what? Take one circuit, take another circuit, you can parallel process the circuits, et cetera, et cetera. I repetitive. Forget about the word families, it's a technical meaning. It's written in the book, whatever it explains, but whatever. These are also bicategories. They are not symmetric. They are not symmetric, okay? Because one of the things we have, I'm going to use the chalk for a second. One of the things you have when you have symmetric, for those of you who can't see, too bad. See, you should have showed up. But one of the things you have with a symmetric is, let's say I do this. I swap the X and Y, okay? And then I swap them again. I swap, I'm doing one process in one thing and one process in another. Okay? So what you need is an eraser. But if you don't have an eraser, I have an eraser, I have an eraser. Okay? Okay, so if you swap things twice, that's the same thing as not swapping at all. Okay, great. Okay, but now let's say you're swapping wires. You swap them again with wires. Okay, that's not equal to this. So again, when you have a physical thing, this is why physicists find category theory challenging, hard, painful. It is because you have to weaken the axioms a lot. So we get something not called a symmetric monoidal category. Symmetric would have this thing that if you swap it twice, but if you try to swap wires and then swap them again, you don't get back the original. You get a knot over there. Hence the word knot theory. So it all shows up in knot theory. Okay, good. We are way behind time. So let's go a little bit quickly. Okay, so you now saw the big picture. Okay. Main point of the big picture, you even have a physical copy of the big picture in front of you. Main point, from the outer spokes, there's functions to computable functions. Okay, so I can summarize this picture as follows. You have Turing machines on top, you have register machines over here, you have circuits over here, you have computable functions. Let's go through it. Given any Turing machine, it goes to a computable function that's describing it. Given any register machine, it goes to a computable function. Given any circuit, it goes to a computable function. Okay. Let's talk about whether or not these diagrams commute. Okay. What are these diagrams going back and forth? Answer, those are compilers. Look, he's good at singing this song, but the point is, you should all be good and you should all be good. Look, if I give you a Turing machine, you could change it into a register machine. If I give you a register machine, you should be able to change it into a circuit. In fact, that's what a calculator does. Think about it. A calculator manipulates natural numbers, and how does it do it? It's got circuits inside. Literally, compilers do this. They take your C Python program and they change it into something that works on a circuit. Okay, so we get this. Now, these things don't necessarily commute out here. Around, it doesn't necessarily commute. And the idea is as follows. Let's say I have a Turing machine. I change it into a circuit. There's lots of different ways to change a Turing machine into a circuit. Okay? I have a Turing machine, I change it into a register machine. There's lots of different ways of doing that. Now I take this one and I try to go there. You're not necessarily going to get the same circuit, but what you will get is the following. These triangles all commute. You have 6 triangles here. Let's go through it. If I change a Turing machine to a circuit, and I get that, so I take that Turing machine and get that function, I better get the same function. I better do the same function. The changing of a Turing machine to a circuit, you better give me the same exact, function. Otherwise, it's doing something else. Okay, the idea is as follows. I don't like this programming language. I want to change it into that programming language. But the program better do the same process. You better do whatever this one did for this input, better do for this one for that input. Okay, so the little triangles commute, but going around doesn't necessarily commute. You don't take into the affect the triangles. Okay, oops. I'm sorry. Okay, I didn't talk about the logic, but there's a logic thing also. Take any of these total things, you could talk about logical formulas. Now, here's another category. Again, I go through it in the book. This category, it's the category of logical formulas. And basically, it depends on how many variables are in the logical formulas. That's going to correspond to your inputs. And it depends on how many logical formulas you have. That's going to be the number of outputs. But basically, every one of these things can be changed into a logical formula. You can have a logical formula that describes the way a program works. That's what this is all about. Okay.
Excuse me.
Go.
I'm sorry. I thought you said there were 6 triangles that were commuting.
Yeah.
I missed 3 somehow.
1, 2, 3. There's 2 arrows.
Oh, I see. Got it. Thanks.
Okay. Don't want to get into this, so I'm going to skip it. Mind? The great host. Big pictures about our computation. So we have this thing here. Okay, main point. You've seen the main point 16,000 times. Everything leads to this middle sign. Okay, now for the rest of the talk, since we know all these things are, we're going to forget about this bottom part. Because I could have done this, but we don't know what register machines are. I could have done with circuits, but those are things that engineers care about. Turing machines, everybody heard of. So let's talk about Turing machines. So we're gonna focus on the top part, the top spoke. So here's the top spoke without any color. Okay, but I'm gonna shrink it because I don't really need. I explained what this is all about. Why we have to talk about this because Turing machines manipulate strings. But I'm gonna get rid of this and we're just gonna talk about the map from here to here. And now I'm talking about computability theory. Okay, so we have Turing machines, total Turing machines. Okay, computability theory, what is that? Tell me when a function is computable or not computable. Computability theory determines if a given morphism in func is in comp func or in total comp func. So if I give you something in here, and the way to think of this is with chalk. Sorry, 1 second. Gotta keep everybody's cameras. Okay. If I give you, yeah,
Before you raise that, may I ask a question?
please.
With wires, is it possible to do the second swapping such that it'll not be entangled?
Absolutely. Watch.
So is there anything wrong with that?
No, no. But the requirement of, so you can do that, but the requirement of a symmetric Monroe category is if you do it once and you do it another time, the same operation twice, you get that.
Okay, thank you.
I'm not, this physicality of wires brings up a whole new world. For example, knot theory can all be discussed from this point of view. Okay, and quantum field theory can be discussed from this point of view. You have objects that are moving a particle around this way and moving a particle around that way. You get this whole. Okay, so we have func, we have computable func, which is just old-fashioned Venn diagrams. We have total computable func. And the idea is as follows: given a certain function, is it here, or is it here? Okay. So computability theory determines if a given morphism in func, so you have something in this func, is it in computable function or a total computable function? Another way of looking at this is to consider the following functors: Turing machines, total Turing machines, and Turing machines, that's this, okay? And they both go down to, this one goes to here, this one goes to here, but they both really go into func. And so you ask if a particular morphism in here, if something in here is in the image of Q, which means it's a computable function, or it's in the image of D, which means it's a total computable function. That's all we're asking. Okay. Just say it. Turing machines are onto this. Total Turing machines are onto this. Give it a function. Is it in here? Is it here? Or is it in here? Okay, so here's a nice function that's not here or there. There's a total morphism in func. It goes nat cross nat to bool. Okay, the function is called halt. This is a function. It's in fact a total function. Okay, if you'll excuse the expression, God knows the value of this function. The question is, can you get a human being to know this thing? Okay, so let's go through this. This is a number. This is a number because they're both natural numbers, and it outputs a bool 0, 1. This outputs 1 if Turing machine Y. This is an enumeration of the Turing machine. So every single Turing machine has a number associated. Okay, every program you ever wrote has a number associated to it. Ready? Take any program in any programming language, save it on a disk, or save it on a hard drive. Okay, what do you save it as? A series of zeros and ones. What's a series of zeros and ones? It's a Boolean number, Boolean integer. That's it. So every single program you wrote has a number. So if Turing machine Y on input X halts, that means it stops. 0 if Turing machine Y on input X does not halt. Theorem, and this is the main theorem. It's attributed to Alan Turing. It just not. I mean, he did amazing things, but he didn't do this. Halt is not a morphism in total computable functions. It's a total morphism, but it's not in total computable. It's partially computable. Ready? You give me a program, you give me an input, you give me a Turing machine, you give me an input. I can sometimes tell you if it will stop. I will sometimes tell you if it will halt or not. Ready? It's hard to say when it won't halt, but I can tell you when it halts. Ready? I run it for a little bit, see if it halts. If it halts, I say, yes, it halted. Okay? If it didn't halt, I have trouble. How do I know it's not going to halt? Somebody was talking to me about the busy beaver problem yesterday. Oh, Pablo, Pietro. Okay, anyways, if you know it's a certain size, you can tell that it's not going to halt either. Okay, good.
So if it's not Turing, who's the author of this?
Martin Davis. But go to Wikipedia page, type in whatever. It's just a shocking thing that everyone thought that it was Turing. Okay, so this is a first example of something that's not computable. Now, I'm not going to prove this theorem. It's not hard. I'm not going to prove it here. I prove it in the book, sure. But I just want to show you the way it looks, the way the proof looks. Okay? And it has something to do with this. You have what's called a decider. What's a decider? It has an input and it gives you a yes/no answer. And this one has, it's called a recognizer. What's a recognizer? It has an input and it gives you a yes, maybe answer. Yes, when I know it's true, and not an answer. Okay. Well, you can combine these to form a decider. You're going to combine two recognizers to form a decider. Anyways, I'm just showing you the way the proofs work. The proofs are basically sequences of morphisms in the category of computable functions. Okay, so again, I'm showing you the shape of the proof, not the proof. But basically, you're going to have, look at this. You have a sequence. You diagonalize, go into both of them. Okay, and you have F composed F. Okay. Again, I'm not going to do a proof now, but the point is the proofs go very, very easy because you're talking about morphisms in a category. Okay, great. Now, so I teach this class in college, and basically, I get to the point where you prove the halting theorem, and the students are big deal. Okay, and the point is as follows. You ready? They say, we've been in school for 16 years learning what computers could do. You find one thing that a computer can't do, and we should be excited about that. Okay. So I have to show you some other problems that a computer can't do, okay? And here's another problem. The non-empty domain problem asks if a given number, the Turing machine, will have a non-empty domain. So what does that mean? So take a Turing machine. Sometimes for some inputs it halts, for some inputs it doesn't. So we call those times when it halts, we call it the domain. The question is, does it have anything non-empty domain? Is there anything in the domain? Does it ever halt? Or does it ever not halt? Okay, and so that's a function, it's called non-empty. Again, give me the number of the program, and I'll tell you 0, 1, whether or not has a non-empty domain or it has an empty domain. Now, it turns out that's uncomputable. You can't figure this out, okay? But the point I want to show is it falls out of the fact that halting is not computable. Since this is not computable, then there's a function here which relates this problem of halting to this problem of non-empty, okay? And then you have computable functions. Then you have composition. The main point is once you have something that's not computable, it's easier to find something else that's not computable, a harder problem. Okay, so what it's called is you can reduce one problem to another. You take one problem and you reduce it to another. And since this one is not computable, this function is not computable. It's a nice function. Again, God knows the answer to this function. This function is also not computable. Okay, so we change from one to another. Okay. Okay, and here I'm saying that again. You have one function that's not computable, and you want to know if another function is not computable. You relate one function to the other, and whether or not this commutes or doesn't is about that. So let me show you some other problems that are not computable. The non-empty domain problem. I should have just said that. The empty domain problem. Tell me, is this function, is the fact that it will never compute, yes or no? The equivalent program problem. Here's something, a cute problem. I teach a class in programs, okay? I teach a class in programming. I teach them some algorithm and I say, okay, for tomorrow, I want you to program it and show me the results, okay? They all hand it in. Question, assuming there's no cheating, okay? Assuming there's no ChatGPT. Where's it goes? There was no ChatGPT 5 years ago. We used to learn how to program. Not that I ever did it well, but we learned how to program. Anyways, so 2 students will hand me in the same program that should do the same function. So question, is there a computer program that I can put in this program into it, put in this program and tell me, does it do the same thing? Let me show you why I would want to do this. I would take the best student in the class, look over her program, see that it works and say, oh, this one does. It does what the function is supposed to do. Now I'll take her program, take everyone else's program, compare. Does this do the same thing as this? There's no way of doing it. Okay, there's no way to get a program to look at 2 other programs and tell yes or no. Are these doing the same function? Yes or no. Now here's a way to start doing it. You say, okay, let's say I input 0. Do they give me the same answer? Yes. Okay, good. Let's say input 1. Do they give me the same answer? Yes, yippee. Input 2. Do they give me the same answer? Yay. Okay, so far it's the same function. 3, 4, 5. But I can do it till 10,000. I don't have an answer. I want to know for every possible natural number. Well, if I input into this program, will it give me the same as inputting into that?
I'm sorry, is it possible to do that in the physical world? Because
No.
it can be monitored where the current flows and see how calculations are made.
I don't see how I'm talking about something infinite.
Okay, so it's
I don't want it to be the same function up to an input 50 billion. I want it to be the same input for any function, for any input whatsoever. So I don't see how a physical process can do that.
okay, I see.
Do you agree with that? Okay. We've been talking about this. Okay, great. Oh, so let's go through some other things. The equivalent program, the printing 42 problem. This is what Turing proved. The printing 42 problem. 42 is just a number that is the meaning of life and everything. How does it go?
The meaning of life, the universe and everything.
Right. It's the meaning of life.
That was way after Turing, right?
Yeah.
So I don't know. Okay, so the idea is as follows. Let's say I give you a program, and I say the program accepts integers and outputs integers. And I ask you, is there an input for this program that will output 42? So I want you to use your computer, I want you to analyze this program and tell me what is it called back engineer. Okay, I want you to back engineer this program and tell me what input I have to give to this program that's going to give me a 42. That's going to output 42. No way in the world a computer could do it. It's amazing. Okay, so Gödel's Rice's theorem says as follows: any non-trivial semantic property of Turing machines is undecidable. The main point here is as follows. You ready? Computers cannot deal with computers. So if you have some property that you wanted to figure out, it can't figure it out. Okay? You can't figure it out. This is all that self-referential paradoxes stuff, okay, which is in the other book, The Outer Limits of Reason. Self-referential paradoxes. Computers talking about computers, something's missing. Okay? Let's talk about something else. Gödel's incompleteness theorem. So this uses that logic part. Any consistent logical system which is powerful enough to deal with basic arithmetic, there are statements that are true but unproven. That is, the logical system is called incomplete. Okay, then there's something called the undecidability problem is unsolvable. This problem posed by David Hilbert asks whether there exists a definite method, computable method, okay, or algorithm that could determine for any given logical statement whether that statement is universally valid, true for everyone. The domain of discourse has to be infinite. If it's finite, just check. True for all possible interpretations. Validity, we talked about that last time. Okay, I always tell this to my students beforehand, you know, again, they spend 16, 17, 18 years learning what a computer can do, and I list off 5 or 6 things that a computer cannot do. Ready? Okay, great. So now I want to do, it's not on the slide, so we'll do it together. Ready? Question, how many computer programs are there? Any language, anything you want. How many computer programs?
Infinity.
Infinity. What type of infinity? We have 2 types of infinity.
Oh.
Accountable, it's that, right?
It's countably infinite. Okay? It's countably infinite. Okay? Why? Because every single computer program corresponds to a natural number. Just save it. Your natural number. Great. How many problems are there? How many problems? Forget about problems. What I want to know is how many properties of natural numbers are there? So let's see, what can we say about a natural number? I can tell when a natural number is even, when it's odd, when it's prime, when it's a member of the Fibonacci sequence, when it's a perfect number. I don't even know what a perfect number is, et cetera, et cetera. How many properties are there of natural numbers?
Uncountable.
2 to the power of n. Because you have yes, no answers for each one of them, okay? And so you have 2 to the power of n. So question, how many properties can a computer determine about natural numbers? I had trouble listing off 5, okay? How many can a computer do? Answer, probably countably infinite. How many properties are there? Uncountably infinite. Okay, the difference between countably infinite and uncountably infinite is vastly, vastly different. The point I'm trying to make is that what computers cannot do is vastly, vastly, vastly larger than what computers can do. Okay, so somebody last class was talking about low-hanging fruit, that all we do is do low-hanging fruit. All you do in computers is low-hanging fruit, because the vast majority of things to do with numbers or with strings or with anything cannot be done by a computer. So we're finite beings living with infinite strings and infinite natural numbers, or talking about them. We don't really live with them, we talk about them, but that world is vastly, vastly, vastly uncomputable. Hence the title of the book. Outer Limit of Reason, what mathematics, computers, and technology or science cannot teach us. So what I show is a lot more. I have a paper on my webpage. It says true but unprovable. It's worth reading. It's a 4-page paper, but shows you Gödel's incompleteness theorem on steroids. Holy cow, we're moving. Great. Complexity theory. So given a total computable function, you want to somehow measure it. How much work is it? How much time? How much things? So there's different things you can measure. You can measure, well, first of all, there's two types of Turing machines. There's something called a deterministic Turing machine and a non-deterministic Turing machine. Non-deterministic Turing machines are like vastly parallel Turing machines. And the two types of things you can measure with them, time and space. How much time does a Turing machine use and how much space does a Turing machine use? They end up in here. Let's say I ask you, how much time does your Turing machine take to solve a certain problem? Okay, and the answer is, you can't give me a number for the answer. The answer is, well, how big is your input? Okay, for example, I want to sort my inbox and my mailing. Well, if I have 10,000 things in my inbox, it's going to take me a lot longer to sort than if I have 100 things in my inbox. Okay, so the results that you get is not a number, but a function from the natural numbers to this. Tell me how big your function is. Tell me how big your input is, and I'll tell you how long it will take, or how many time steps it will take, or how much space it will take to solve it. Okay, so these are the way you measure things. Hold on. Okay. Once you measure, so these are measures. Once you measure things and you have a subset of such functions, okay, then you could talk about. So this is a subset. This says, okay, I want to measure these small sets of functions. I want to see how much I get. So then what you have is this thing. So this measures deterministic Turing machines in time. So I have deterministic time machines of functions in S. Okay, and so here's all total computable functions. This is a subcategory of it, namely the same types, all types, whatever, but here the measure won't be using more than S. So there's a way of restricting. I don't want to talk about every single type. I want to classify and classify how these things are. So we have that. Okay, so we have deterministic space, non-deterministic space, et cetera, et cetera. Okay, so we're going to go through complexity theory a little bit quicker. Basically, there's three ways of measuring, of comparing how you measure things. So for example, space and time. Let's go through this. Let's say I need 50,000 memory boxes to, and I need 50,000 memory boxes to calculate some function. Well, guess what? If you need 50,000 memory boxes, you definitely need 50,000 time steps to fill those memory boxes. So whatever takes you a certain amount of space, it's going to need more time for it to do. Obviously, when you're calculating, you might go erase a certain memory box. If you need 50,000 memory boxes, you might have to erase things, et cetera, et cetera. Okay, so not only do we measure how long things take, but we also measure how much space things take. So this is part of complexity theory. This shows up in, let's say, the game of chess. Okay, how come chess wins so much? Computer chess wins so much because if you want to play chess, what you have to do is as follows: you have to pick a move such that the computer is going to pick a move such that he's thinking about what I'm going to move, and I'm thinking what he's going to move. He's thinking of what I'm going to move. You're going to get a tree that's 10 long. And if you think about it, in chess, every single board has about 30 possible moves you can make. So you're going to have a tree of 30 by times 30 times 30 times 30 times 30. You need save a lot, you need a lot of space to win chess. Okay, deterministic versus non-deterministic, these are these fancy computers that do things massive parallel. The point is, deterministic is easier than non-deterministic. Subsets versus sets. I'll show you what that is. Okay, so here's a nice diagram that shows you, I told you what complexity theory is all about is classifying these total computable functions. So let's go through this. On top, you have two sets of functions, t, which is smaller than s, and you have that. Okay, so the top is all about s, the bottom is all about t. The left is all about determinism. The right is all about non-determinism. The front is about time. The back is about space. So basically, all of these are leading to here. Those things that need non-deterministic space, that's a lot. These are a little, okay? And we can go on, we classify these problems one after another. You can also talk about different types of functions, constant functions, logarithm functions, polynomial functions, exponential functions, okay? And this is what you do in complexity theory. You say, okay, this algorithm takes an exponential amount of time. This algorithm takes polynomial amount of time. This algorithm takes logarithm amount of time. Okay, and you get big things like this. And again, I can go through it. So this side is here, you're building a constant log, poly, exponent. And you have a nice way of describing and classifying all these different types of functions. All these are subsets of total computable functions. Okay, and you can change one function into another function. I'm sorry, you can change one problem into another problem. So these are called polynomial reducible. And you could talk about those things that take polynomial time and those things that take non-deterministic polynomial. So this is the P is equal to NP problem. Okay, and so we have a nice way of formulating. The idea is as follows. These are both in total computable functions. This is the set of all functions that can be done in polynomial time. These are the set of non-deterministic machines that can be done in polynomial time. We know that this is a subset of this. The question is, are they equal? Let me explain to you why it's an important question. The question is as follows. We have easy problems and we have hard problems. Question, is there a trick to solve a hard problem so that it becomes an easy problem? That's what the P is equal to NP problems. And this is considered the hardest problem in computer science. Okay? Many people believe that there are certain problems like the traveling salesman problem, which is a very hard problem, but there's no trick to doing it. Okay? But nobody's proven that there's no trick. What they say is as follows. Problem's been around for about 70 years and no one's found a good way of solving it, not even in Wolfram. Not even in Wolfram research has they found a way of solving it. So it must be that it's not true. Okay, but I'm not convinced. Well, anyways, so people think that P is not equal to NP. Some people think that P is equal to NP. I'd like to show you how category theory is related to this. Okay, so this is okay. So those of you who aren't, read this, but not now. Okay, is the P is equal to NP question. So let's just go through. I want to explain to you how category theory is related to it. Not that it's going to solve it, but we know that P is a subcategory of NP. So let's go through that. P is the easy problems, NP is the hard problems. Well, are hard or easy. If P is P equal to NP, so this is $1 million question. So in 2000, Clay Institute came out with 7 questions, hardest math questions in the world. And one of them is the P is equal to NP problem. If you have a solution, come speak to me about it. Don't tell anybody that you're coming to speak to me. Okay, so it's $1 million. By the way, one of the problems was solved already. So the pressure's on. If you're going to do it, you better do it this weekend. Okay. One of the problems was solved. The Poincaré conjecture was solved. by a guy whose name I can't remember right now.
Gregory Perelman.
Gregory Perelman, who didn't accept the money, so I wonder if the other money goes. By the way, there's a way for you to get not, so if you solve the P is equal to NP problem, you get $1 million. But there's a way for you to get actually $6 million. Okay, and the idea is as follows. Every one of the other problems can be written as a logical problem in a logical format. Okay, and then one of the things that you can do if P is equal to NP is that you can find proofs of statements very easy. Okay, so let's go through that. Usually you think of, given a proof, I can easily check if the proof is right. But finding a proof is a hard problem. It's an NP problem. Okay, but if you were able to prove that P is equal to NP, then not only could you get the $1 million for proving that one of those problems, but you can plug in all the other problems like the Poincare, the Navier-Stokes problem, which is something physicists spend time with, and different things like that, and you can get all the other, you can solve all the other problems because you were able to find proofs very quickly. Okay, but don't spend a lot of time. Okay, we are not claiming that category theory can solve the problem, but category theory has what to offer for the root problem. This is more in a way of a dream than a research project. This is what keeps me up awake at night when I can't fall asleep. Okay, first some preliminaries. Okay, every problem has what's called a search space. Okay, there's usually associated a search space. For example, the factoring decision problem. So if I give you a number and I ask you factor it, I'm sorry, not asking you whether or not it's prime. That was done in 2003. What I'm asking you, give me the factors of it, or are there factors within a lower number? Okay, that's considered NP complete problem. That's an NP problem. Okay.
I don't think it's NP complete,
It's not NP complete, right?
but it's harder than P probably.
Right. It's not NP complete, and that's why Shor's algorithm can solve it, because quantum computers is another area. Quantum computers can't solve NP at all. It's believed that quantum computers can't solve NP complete problems, but it's okay. So factoring problems, basically the given a number, give me a factor for that number. Okay. Now, the possible places where you can find the factors is all numbers from 1 till that number, 2 till that number. So that's the search space for it. One of these numbers might be a factor of the. Okay, let's tell you about the traveling salesman problem. A man wants to travel to N cities. He has a distance between any 2 cities that he wants. He wants to get the minimum distance. Okay, turns out that if for N cities, the search space is N factorial. It's a humongous one. And you want to see if you have a small, if there's a way to travel every city and come back to the original one in a short amount of time. Okay, the knapsack problem is as follows. You have a knapsack. Okay, you want to fill it up with N things. You have N things. You want to fill it up with some of those N things, such that it fits in your knapsack, but it's large. It's each thing that I get is the most expensive. Okay, that has a lot of things, and it has 2 to the N things in its search spaces because there are 2 to the N possible subsets of N things. So these have humongous search spaces. When a computer solves a decision problem, it searches through the search space. Okay, very nice. Okay, many times the search space is small and the computer can find the solution with ease. We call those P problems, or P. Other times the search space is large, but there are tricks to find the solution with ease. In other words, if the search space has a lot of structure, we use that structure, like the natural numbers, we use that structure to find the solution quickly. Okay? And still other times the search space is large and only a lengthy brute force search will find the solution. Those things are called NP problems. So traveling salesman problem is notoriously difficult. Okay, in my other book, I calculated how difficult it is. Let's say you have 100 cities. Okay, let's say you have 100 cities and you want to see, and you want to visit every one of those cities. Let's say in the United States, you want to visit every one of those cities and you want to find the shortest possible route. How many possible routes do you have to search in order to find the shortest possible route? I'm not asking you what the shortest possible route is. I'm asking you how long will it take you to find it? Okay, and the answer is it depends how fast your computer is. But let's say your computer can check 1 million routes in a second, which is not unheard of. How long do you think it will take you to search for those possible routes? Any guesses? Let me give you an example. If I had 6 cities, I would have to check the 720 possible routes, 6 times 5 times 4 times 3 times 2. And if your computer can do 1 million in a second, it won't take that long. If you have 10 cities, it'll take something like 3 seconds. Question: how long will it take to do 100 cities?
We're never finishing.
9 times 10 to the 151 seconds.
-1.
Okay.
The answer is, usually when I ask this question, I usually get the 2 weeks, no, 3 weeks. The answer is 10 to the 142 centuries. That's how long it'll take you to calculate what the shortest possible route is.
Yeah.
10 to the 142 centuries. Okay. And so that's a humongous amount. And you could say, oh, I know Professor Yanofsky, he wrote a book on quantum computing. I'm going to get a quantum computer to do it. No, a quantum computer can do it in 10 to the 72 centuries. Okay. And multiprocessing is not going to help you in there are certain things that are the limits of man's ability to know. Okay. Okay, so back to category theory. How is category going to help you? There is an intuition about the difference between problems in P and problems in NP that goes as follows. Problems in P have well-structured search spaces. Programs that solve problems in P use this structure to find solutions with fewer operations. In contrast, problems in NP have search spaces that do not have a lot of structure. Programs with such problems have to hunt through a lot of search spaces because there's little structure to exploit. It should be noticed that even for NP problems, search space usually has a tree structure. So you want to search through all possible n factorial possible routes. There's usually a tree structure and you have to do backtracking. That's what kills you. Backtracking is what makes it an exponentially hard problem. It should be, okay, however, this structure is not good enough for there to be a program for finding the solution quickly. It doesn't have enough structure. So again, P problems have nice structured search spaces. NP problems have not nice structured programs. Okay, it would be wonderful if this intuition was formalized into clear statements. I'm BSing you. I'm making this up as I go along. Okay. This is where category theory comes in. Over the past few decades, category theorists have classified and categorized many different things in describing structures. They have invented hierarchies of algebraic theories. This is what category monads, operads. This is what category theorists, this is their bread and butter. They talk about this structure and that structure and that structure. It would be nice to classify what type of such structures defining devices produce search spaces that are in P as opposed to NP. This will give a purely syntactical way of describing what is in P and what is in NP. I'm not sure it's going to solve the problem, but if it does, thank me and they acknowledge. Okay, 15 minutes. So I told you there's a theorem called Levier-Cantor diagonalization theorem. I don't want to get into it. That's the statement of the theorem. Let A be a category with a terminal object. I don't want to get into it. Then there exists a et cetera, et cetera. Okay, that's it. And then there's also the contrapositive of the theorem. If A implies B, then not B implies not A. So that's the conclusion. I'm talking about it. Almost every instance of self-reference and diagonalization proof falls into this simple format. Okay, and a lot of things fall out of this one quick statement, easy to prove in category. Okay, so here's some applications of this one quick theorem. There does not exist an onto function from the set of natural numbers n to the power set of natural numbers p of n. That's Cantor's theorem to show the difference of what you were just talking about, the difference between countably infinite and uncountably infinite, can be proved with that. That's a diagonalization proof. The unsolvability of the halting problem. I did that before, but you can do it here. This is all about self-references. You have computers talking about computers. You have self-reference, therefore you have a problem with what it's doing. There's a computable function that's not primitive recursive, whatever that means. There's a total linear functions that's not computable. The recursion theorem, these are high-powered theorems in theoretical computer science, but they all fall out of that two-sentence theorem of category theory. The space hierarchy theorem, which says there are computable functions which can be computed in space of H, but not in less space. It needs H space, and it can't be done. We can say when something can't be done in less time. Less space. Time hierarchy theorem. There are computable functions which can be computed in time of H, but not in much less time. So this word much is put in on purpose. Okay, for those of you who know about something called oracle computation, there's something called the Baker-Gill-Sullivan theorem. It says that if you're dealing with something called oracles, then sometimes P of A can equal to NP of A, and sometimes P of B is not equal to NP of B. So if you include extra information, sometimes the P equals NP problem can be solved this way, sometimes it can be solved. Okay, there's another theorem called Labner's theorem. It says as follows: if P is not equal to NP, then there are an infinite number of complexity classes between them. So either they're equal or they're very distant. Okay, in 2003, I published a paper called, so this is before this book, A Universal Approach to Self-Referential Paradoxes, Incompleteness, and Fixed Points. It's in the Bulletin of Symbolic Logic, and it has 19 different instances of this theorem. So this self-reference goes way beyond just theoretical computer science. Russell's paradox, Grelling's paradox is about language. The liar paradox is about language. The strong liar paradox, language. Richard's paradox is about numbers, and Turing's halting problems, which I did before. I'm sorry, I did this in this book. We did this here. Gödel's first incompleteness theorem. Gödel's incompleteness theorem is about language. I'm sorry, it's about mathematics, talking about mathematics. Whenever you have something talking about itself, you get that, you get a problem. Okay. Tarski's theorem says, Gödel's theorem says there's a problem with provability. Tarski's theorem says there's a problem with proof. Parik's sentences, he talks about length of proof. Very nice result. Rice's theorem, we talked about it. Von Neumann talked about self-reproducing machines. Time travel paradoxes. What's time travel paradoxes about? Okay. Let me, you all know, if you've ever watched a science fiction movie, these science fiction movies are either about time travel paradoxes or about computers that take over. And this is why Terminator is so exciting, because it has both things in one. Wow. Okay. Okay. So usually, if usually an event, one event will affect another event. So if I give a good class, you're going to smile. Okay. So one event gives another event. If I let go of this card, it falls to my hand. One event affecting another event. Time travel paradoxes is one event affecting itself. Okay. Mm-hmm. So in Back to the Future, what's the guy's name?
Marty.
If Marty goes back and gets his mother not to like his father, then Marty's not going to exist, and Marty won't be able to go back. Okay, it's a very sick movie, actually. This is called the grandfather paradox. If you go back in time and kill your bachelor grandfather, then you won't be born, and you won't be able to go back in time and kill your bachelor grandfather. So it's an event that affects itself. Right? And it doesn't exactly fit in, that's why it's parentheses, but it almost fits into our formalism. things. That means self-referential paradoxes. By the way, you don't have to get violent to get a time travel paradox. One of the world's easiest time travel paradox. Ready? So you walk. Here's your time travel machine. Okay, Doctor Who. You open the door. You go into the time travel machine. Close the door. Okay, in your time, I want to go 1 minute earlier now. I don't want to go travel 10,000 years away. I want to go 1 minute earlier. Okay, so you go 1 minute earlier. Now you're in your time machine. You press the button and you go. You're in the time machine. And now comes in your earlier self. And he wants to enter the time machine to go 1 minute earlier. And here's what you do. Hold the door closed. Hold the door closed. He, your earlier self, can't come in to hold the door closed. That's it. That's the only part of the time machine. Okay. So what's going to happen if you're successful at holding your door closed? If you're successful at not letting your earlier self in, then you will not exist. Okay. And then your earlier self will be able to go in and make sure that your earlier self does not get in. Which makes sure that back and forth. Okay, without killing anybody, you know. I don't know. Seriously, if you think about it, go back and kill your bachelor grandfather. What type of people are think up of this? Okay. Other fields of theoretical computer science. You know what? I'm just going to go through this quickly. I'm just going to talk. Okay, so I'm slowly going through. These slides. Basically, I'm telling you what a cryptographic protocol is, and most cryptographic is from the category theory point of view. You see arrows and vertices. You have subsets of arrows called hard and soft, and they have to satisfy that commutative diagram. I just want to talk about what algorithms are from a categorical point of view. Okay, and the idea is as follows: these are computable functions. Okay, and so you have. Let's say you have a computable function called sort. It accepts n numbers, sorts them, and returns them in the sorted list. Okay? And you have another computable function called find max. What does it do? It accepts n numbers and returns the largest of the n numbers. Okay? Now, let's say you were to write a program that did this, or let's say you taught your class how to do this. So you would say, look, here's merge sort done by Alice. Here's merge sort done by Bob. Here's quick sort done by X. Here's quick sort done by Y. So here's 4 different programs that give you the same function, sort. Okay? 4 different programs that give you the same function. Here's find max. There could be a lot of different programs to give you this find max. How do you find the maximum element? Okay, so what you have to see here is you have to see 2 levels of things. You have computable functions and you have programs that describe these functions. By the way, we've been doing this all along. This function from programs to functions, that's this thing from Turing to compfunc. We've been talking about this all along. Main point is it's a surjective function. There are a lot of different programs that give you the same functions. Great. Now, question. I know what a program is. I know what a function is. What the hell is an algorithm? Okay. And the answer is an algorithm is an equivalence class of programs. They're a way of bundling together, same word, bundling together different programs so that the same one. For example, you have 2 different merge sorts, so they're and they go to sort, but all the programs that describe merge sort is one algorithm. And all those programs that describe one quicksort, merge sort and quicksort are 2 different algorithms to describe the same function in many different programs. So what you have is programs, algorithms, and functions. Programs is an onto functor to algorithms. to computable functions. Again, this is a symmetric monoidal category. This is not. This is just a graph. It's not, I mean, it's a graph, it's whatever. It's not as pretty as that. This is more physical, more abstract. Algorithms are somewhere in between. Okay, and this is an interesting thing, and it's somewhat, okay. Question, when are two programs really giving you the same algorithm? Somewhat of a subjective question. It's not clear. I wrote a few papers about that, but thanks. Okay. Lessons learned. Well, look at it. Look at it. Okay, this is the song, so we like singing songs. So every Turing machine is equivalent to a Turing machine in Turing 1.1. Okay, in other words, one input, one output, or just one input and out. Okay? Every logical circuit has an equivalent NAND logical circuit. Okay, now I'm going to make a few statements about theoretical computer science, but the point is they all have that same feel for it. It's the same song. Every non-deterministic Turing machine has an equivalent deterministic Turing machine. So everything that NPN can do, non-determinism can do, determinism can do. Savage's theorem. Savage's theorem is about polynomial space and polynomial and n polynomial space. Okay, deterministic versus non-deterministic. We saw the big question in computer science is what about time? But let's say we talked about space. Let's say we measure space. Well, Savage's theorem says that anything can be done in non-deterministic space can be done in polynomial space. So in deterministic space. So the point is it's solved for space. It's not solved for time. It's a major thing. We're very good. Okay, these are three other types of things. Well, guess what? We can formulate all of these in one simple picture in category theory. There we have. All these can be described as the following density relations. So let's say this. You have a subset of things, and you have a bigger set over here. And what are we saying all the time? The first time was a Turing machine with n inputs and m inputs can be done by a smaller Turing machine with one input and one output. Okay, so what that says is there's a function from this big thing down to this thing. Now, this is not an isomorphism, this is not anything. Smaller Turing machines are, or more restrictive Turing machines are smaller than big Turing machines. But there's a way of going there. Now, what does it mean that every Turing machine can be done, every non-deterministic Turing machine can be done with a deterministic? They all have to respect this function here, where they have to be able to produce the same function. I take a non-deterministic machine, I want to create a deterministic machine that does it, but it better as hell preserve these triangles. It's just like before, we were talking about the triangles, preserving these triangles. It has to preserve these triangles. But one commutes and the other one commute. One way, you start here and you go like this, that can commute, but going like this and going like that doesn't commute. So this one nice picture summarizes all those other instances of singing that song. Whatever this can do, that one can do. Okay, it's amazing how once you see it. So again, we proved many versions of this. But once you see it, it becomes, it's the bird's eye view of everything. Okay, that's it.
Nick.
You need a ride to Brooklyn or something?
Questions? Also from people on Zoom, if you have any questions, now would be the time to ask.
Speak now or forever hold your peace. No, anyway, send me an email. I'm sorry, go.
Can we relate it maybe to yesterday's lecture a bit?
Perfect, and we should bring in the Rulliad. Okay, because if I'm going to talk about the category of all Turing machines, I should definitely bring in the Rulliad. But if I don't, it'll still be nice to me. So I don't have to. So what did I do today? Okay, what I did was I took the category or the collection of all computable functions and I found a nice structure to look at them as. Okay, in other words, they all exist, but we found a nice way of looking at all of these different structures and classifying them and categorizing them and seeing whether they can be this way or they can be that way in a nice systematic way. Another thing we did was we kind of showed, this is in relation to the other talk, finding order and randomness. We kind of showed that really what we're doing in life is the low-hanging fruit, okay? Because the vast majority of things are way beyond it, okay? We have uncomputable functions, which means things that computers cannot do at all, and we have unfeasible functions, which take very, very long to do, or need a lot of resources.
So if you connect that to this whole idea that if we want to understand or explain more and more physical phenomena, and the less and less restriction by mathematical axioms, it seems counterintuitive to the monoidal
Right.
categories because they add more and more structure. Like,
Right. So the point is when you get to, so computable functions are very, very, not concrete. They're very, very abstract objects. They don't exist. They're not physical things. So we can swap them with ease and we don't have to worry about crossing wires and we can compose them with ease, okay? But when you get to physical objects, and by the way, that's an interesting thing, all computation has to be done with a physical object. The result is a mathematical object, a function, but computations are about physical objects. This is this thing that information is all physical, okay? So let's go through it. The more physical you are, the less axioms you satisfy in your category. Okay. So a symmetric monoidal category is a very, very tight structure and it has lots of requirements we had up there. But you have to weaken this to talk about physical things. Let's talk about commutativity. Okay, we all know that A times B is equal to B times A. Everyone knows that. Okay, as physicists, you deal with matrices. Okay, you don't call them matrices, you call them tensors. You feel good about yourself if you can do that, but you deal with matrices. Okay, and the main point about matrices is they don't commute. Matrix multiplication doesn't commute. So that's a weakening of that type of axiom that you're dealing with, but you're able to deal with a lot more physical things when you're dealing with it. Okay? You wouldn't want to take away matrices from physicists. They spend a lot of time talking to them. Sorry, tensors.
so what type of physics do these monoidal categories then, or symmetric monoidal categories relate to?
You want to do that?
Well, the ZX calculus is all about monoidal categories, and that's the heart of quantum computing. For example.
In this book on monoidal category theory, I have a mini course on quantum computing. Okay, and it fits in very nicely because what's quantum about? Quantum is about Hilbert spaces, right? Or I'm sorry, it's not about. Quantum is about some type of phenomenon, but we describe them with Hilbert spaces. You take tensor products of Hilbert spaces, you take tensor products of quantum systems, right? And you manipulate them and you use them. Okay, and so you're going to have from this category of circuits. You're not going to talk about the category of circuits. You're going to talk about the category of quantum gates. Okay, and you have to look at what type of structure that has. Okay. By the way, I wrote a book on quantum computing. It's called Quantum Computers for Computer Scientists. And it doesn't mention the word category theory, but it's all about category. I'm from. You have to think category theory.
So just building up on that and relating what you mentioned yesterday about the laws of physics and the lawlessness, would it be suggestive enough to say that the laws of physics are simply the tricks that you mentioned or the heuristics within a P space? And all the things, all the problems for which there is no structure that sit in the NP space, for that we don't have anything. So now I'm just translating to the physical world. So laws of physics are simply statements about tricks in P space, and everything else is unknown.
I don't like. Yeah. So why do we talk about polynomials? First of all, I don't know, because polynomials, when you have something like n to the 15, okay, it's a polynomial, but it's unfeasible in every sense of it. Okay, you can't solve anything with anything as well. So I don't like to divide opinion. Talking about physics. And also, I think things are a little bit messier with physics in the sense that you can do certain things. And I think you were talking about this, like with calculus is doing infinite processes. When you're taking a derivative, you're doing an infinite process in some sense. So I'm nervous about this, that saying physical laws are somehow only related to
Fine. In that,
polynomial.
okay. So in that case, the law versus lawlessness dichotomy, which space would you place that in?
That's a heavy question. I know, it's the minute you get into categories, you're already talking about laws. You're already talking about structures. I'm saying there are large things that can't be put into categories. Right, so now we're getting to metaphysics. You know, the things that we can calculate, the things that exist, it's different levels there. You know, he's pushing me into a corner. I agree with everything you say, but go.
In category theory, there are certain shapes of arrows that we use in order to indicate that we want to think about a relation in a certain type of way. Like there's the curved arrow for the subsets and there's the barbed one for inclusions. Are there any others that we should keep at the front of our minds?
So let's talk about functions for a second. You could say about functions between two sets, usually you have two properties about them that are fundamental. Injective, which just means one-to-one, or surjective, which means onto. Okay. So with functors, there's like 5 different things. Okay. So first of all, you could talk about on objects. So functors so categories have objects and morphisms between objects. Functors take objects to objects, morphisms to morphisms. So now we have 2 things to worry about. Okay, so now we can talk about objects. So we can say a functor is injective on objects, inclusions, or surjective on objects. Okay, and a lot of times in here it's going to be identity on objects. Means takes every object to the same object. Okay, and then you have for the morphisms, you can also have something's called full, faithful, and then fully faithful. So full means pretty much injective on morphisms. I'm sorry, full means onto on morphisms. Faithful means 2 different ones go to 2 different ones. That means into on morphisms. So already you have, 3 possibilities for morphisms, 3 possibilities for objects. full faithful, injective, surjective identity or isomorphic, whatever. And so already you have 9 different ways of talking about this. So usually the only thing is the inclusion is the inclusion, then onto is double-headed arrows. And then they make different symbols on it, equivalents of categories and isomorphic of categories. Because you have a lot more structure, you can talk about a lot of different subsets of those structures.
Other questions?
The minute we go, when we finish, we can go eat.
Right, thank you.
It's been a pleasure. Thank you very much.
Thank you for
Seriously,
coming.
thank
you.
Thank you.
I was trying to think of a way that you could have built the title of this reference book.
There you go.
I was trying to think of a way that you could have been self-referential. I thought the book on self-referential paragraph.
So in my other book, I have this reason I talk about, in the index, I have a place about self-referential paradoxes, the index paradox of self-referential. Anyway, so I do have some type of infinite loop.
Yeah. Reminds me of those like Linux programs that are recursively named with the first letter in the acronym is the acronym again.
So thank you very much for the lecture. I wanted to talk with you because it's kind of related to my project here, because I'm working on a research paper that construct. I mean, they don't focus too much on this paper, but they construct a function. Theory of partial.
Yeah, it's the rhombic tetrahedron.
Yeah. It's very nice.
I know that, but I mean,
Yeah, you go to the desk in the dorms, and they have some behind the desk. It's really cool.
Yeah,
You want?
so in case.
I have this one.
I don't. They use this idea.
You have what one?
Yeah.
Properly saved, but